Okay, greetings. So let's get started with today's class. So a quick recap of what we did in the previous class. We looked at the various components of a gearbox. We looked at the construction and also the operation of what was called as a synchromesh gearbox, and we looked at the concepts of gear engagement, through what is called as a synchronizer, right? So that's something which we learned in the previous class. So the role of the synchronizer is to ensure that the gear engagement is smooth, when we essentially are engaging an output gear to the output shaft, right, that are initially rotating at different speeds. So we also looked at how a multi-rail selector is used to select a particular gear, right. So this is where we stopped in the previous class. So in today's class I will get started with powertrain analysis. So having looked at how a manual transmission is realized and is operated, so let's look at how do we analyze such a powertrain and how do we select first cut values of various gear ratios for a multi-speed gearbox depending on vehicle performance requirements. So that's an analysis that we are going to do. So if you look at the flow of energy, like in a powertrain that we are considering. So let's say the engine delivers a torque Te at a speed omega E, and that's transmitted to the flywheel. The clutch engages with the flywheel, right, and let's say it transmits a torque T subscript T at a speed omega T. Okay. Of course, when the clutch is rotating with the flywheel without slip, omega E and omega T will be the same, right, and this is then transmitted to the primary gearbox. So N subscript T is the gear ratio of the primary gearbox, whatever gear that has been chosen, okay, and the primary gearbox outputs a torque T subscript D at a speed of omega subscript D, which goes to the final drive. The gear ratio of the final drive is denoted by N subscript D. Oh, sorry, this is not the this is the gearbox gear ratio of the selected gear. So N subscript D is the gear ratio of the final drive. Okay. And the final drive transmits a torque Tw at a speed omega W to the wheels, which is then realized as a force, traction force F, at a longitudinal speed V. Okay, so this is the traction force that is provided by the powertrain to the vehicle. This is the vehicle longitudinal speed. So we can see that a typical powertrain transmits energy through these set of components, right. So this is the gear ratio of the chosen gear in the primary gearbox. Now what we are going to do is that we are going to relate all the terms that appear in this block diagram to get an idea as to what will be the output from the powertrain, for a particular chosen gear and a particular input engine torque. Okay, so that is our motive. So in this analysis, what we will do is that we shall lump and account for friction losses at the end. Okay, so we will not deal with the friction loss at each and every component, but we will look at the friction, we will account for friction losses in the entire powertrain as a transmission efficiency at the end. Okay, friction losses through the transmission efficiency parameter. So that is something which we will look at later. All right. So now we will come one component at a time. Okay. So the first equation that we are going to write is for the torque input to the primary gearbox. So, the torque input to the primary gearbox is given by T subscript T, which is nothing but the input torque T subscript E minus the inertia of the rotating components, right. So, the engine and the clutch components. So, let us lump them as some IE times alpha E. Okay. So, where alpha E is the corresponding angular acceleration. So, we are not considering the torque due to friction, viscous friction right now, because as we just discussed, we will account for all the frictional losses at the end. Okay. So, we are only going to consider the inertial term, okay, when we are relating the input and the output torque of each block. Okay. So, this is the torque input to the primary gearbox. Now, next comes the torque output from the primary gearbox that is given by T subscript D, which is what is going as input to the final drive, and that we can write as the input T subscript T minus the inertia of the rotating components in the primary gearbox, which is taken lumped as IT alpha T, and we are essentially going to multiply it by the gear ratio N subscript T, okay, because there is an scaling taking place, right, due to the gear ratio. So, that is how we are going to write this equation for the torque output from the primary gearbox. So, that is TD. So, now this torque is going to go to the final drive. So, the torque output from the final drive can be similarly written. So, the torque output from the final drive is now going to be that is represented as TW, because the output from the final drive is denoted as TW. That is going to be the input torque minus the inertia multiplied by the corresponding gear ratio, right, ND. Okay. So, that is going to be T subscript D, which is the input, minus ID alpha D times ND. Okay. So, this is what is coming out of the final drive. Next, from the final drive we go to the wheels. So, this is what is going as input to the wheels. So, the tractive force F available at the so called tire rod interface of the wheels from the powertrain, okay, is F, which is going to be equal to TW minus the inertia of the rotating components of the wheel assembly. This is the torque which is coming out, divided by the radius of the wheel assembly, okay, that will give me a force, all right. So, along the longitudinal direction of motion, okay. So, this is going to be the force at the wheels, okay, that can be used for driving the vehicle, and this is coming from the powertrain, okay. We are also going to look at what is required from the vehicle's perspective shortly, right, okay. So, now what we are going to do is that, like, shortly we are going to learn about what is called as wheel slip and wheel slip ratio, because in road vehicles, if you look at the tire, the pneumatic tire, what happens is that it sticks and slips at the tire rod interface. So, it is not undergoing a pure rolling motion. So, there is something called as wheel slip, which becomes very important, okay, and that has a very strong impact on the tractive force limit available at the tire rod interface. we shall look at it more closer, particularly when we are looking at braking analysis and anti-lock brake systems. Okay. So, right now we will, for this analysis we will not consider wheel slip ratio, okay, and then like we will write down simple equations. Okay. So, we will neglect slip at the tire road interface to obtain the angular acceleration of the wheel will be the longitudinal acceleration of the vehicle divided by the wheel radius. Okay. So, by neglecting the wheel slip. Okay. So, this is nothing but longitudinal vehicle acceleration. Okay. So, that is alpha w. Now, we go backwards, okay, in the reverse sequence as far as the components are concerned. So, if alpha w is the angular acceleration of the wheels, which is at the output of the final drive, what do you think is going to be the angular acceleration at the input to the final drive? We essentially use the definition of gear ratio, right. Gear ratio is the ratio of the input speed to the output speed. By using that relationship, how can I write alpha d, which is essentially the angular acceleration, the final drive, that is going to be equal to nd times alpha w, because nd is the gear ratio of the final drive, right. So, similarly, what will be the angular acceleration alpha t, which is at the input to the primary gearbox, that will be the corresponding gear ratio nt multiplied by the angular acceleration of the output shaft, okay, which is alpha d. So, alpha t will be equal to nt times alpha d. This we can rewrite as nt times alpha d is nd alpha w, okay. So, typically the product of nt and nd is represented as ntd, okay. So, n subscript td is nothing but the product of the two gear ratios nt and nd, okay. So, this is what we will get. Of course, when there is when the clutch and the flywheel rotate as one unit, alpha t and alpha e will become the same, right, because it is rotating without any slip, right, when the clutch is fully engaged and the entire flywheel clutch assembly is rotating as one unit, okay. So, that is something we remember. Now, we put together all these equations, okay. So, that is what we are doing. So, the equations for the torques and equations for angular accelerations we are going to simplify, right. So, let us do that simplification. So, using all the above equations, the idea is to get this equation for f. So, f is going to be equal to nothing but Tw by Rw minus Iw by Rw times alpha w. What is alpha w? It is nothing but A divided by Rw, right, we just observe that. So, what am I doing? I am just taking this equation and rewriting it. I am just substituting for alpha w, right. Now, we go up and then substitute for Tw. From where do I get Tw? From this equation, right. So, Tw is going to be equal to Td Nd, right, divided by Rw minus Id alpha d Nd divided by Rw and Iw A divided by Rw square remains as it is, right. So, what we have already got in the previous step. So, now I hope you get the idea, right. So, we keep on substituting for each variable and eliminating them. Now, what is alpha d? Alpha d we can essentially, I am writing here, alpha d is nothing but nd times alpha w, and that is nothing but nd times a divided by rw, right. So, that is a substitution we will make. Then what do? We go and substitute for Td, from which equation can I substitute for Td? Here, right. We already have an equation for Td. So, let us go ahead and substitute for Td. So, this is going to be Td is T subscript T Nt Nd, right, divided by Rw minus, what do we get? We get It alpha T Nt Nd by Rw. That is the first term in the previous equation. This becomes Id Nd squared A divided by Rw square, right. So, this term, once I substitute alpha d to be Nda by Rw, we will get this equation, and Iw times A Rw square remains as it is, right. So, that is what we get. Now, what we do? We essentially simplify further, right. So, we essentially simplify for alpha t. What is alpha t? Alpha t is Ntd alpha w. From where did I get this? From here, right. And we already know that alpha w is going to be A divided by Rw, and this Nt times Nd is going to be another Ntd, correct. So, that is something which we can immediately figure out, okay. And this Nt times Nd is also going to be equal to Ntd, right, okay. So, now what we do is that, like, we have to substitute for T subscript T. So, what is T subscript T? If you recall, T subscript T is going to be equal to, if we go back, T subscript T is going to be equal to Te minus Ie alpha E, right. So, let us substitute that. So, this is going to be equal to Te Ntd divided by Rw minus Ie alpha E Ntd divided by Rw minus It. What we are going to do is that we are going to rewrite this as Ntd square A divided by Rw square minus Id Nd square A divided by Rw square minus Iw divided by Iw multiplied by A by Rw square, right. So, that is it. So, now we just need to eliminate alpha E. So, when the flywheel, the clutch rotate as one unit, we just discussed alpha E is going to become equal to alpha T, and what did we just simplify for alpha T is going to be Ntd times A divided by Rw. So, that is something which we have already done, right. So, now if we put all these things together, so simplifying these, we are going to get F to be equal to Te Ntd divided by Rw minus, let me collect all the terms together, Ie plus It times Ntd square plus Id Nd square plus Iw multiplied by A divided by Rw square, okay. So, this is what I will get as the final expression. So, this is an expression that relates the force that comes out of the powertrain to the input engine torque and the gear ratios, okay, and the inertia of the rotating components and the acceleration, right, of the vehicle. Okay, so that is what we know. Now, here we will put an factor eta t. Okay. So, as I discussed, we lump for the all the frictional losses, right, as a transmission efficiency. So, at this point we introduce a parameter eta t, which is nothing but the transmission efficiency. So, we introduce it here and this is what we would get. Okay. So, as an expression for characterizing the powertrain, a simple expression, right. Please note that if the vehicle is cruising at a constant speed, what will happen to A? Note that if A equals 0, that is the vehicle is cruising at a constant speed, we will just get F equals T NTD eta t divided by RW. Okay, so this is what we will get. Okay, so please remember this, we will use it later on. Okay, so this is from the perspective of the powertrain.